Yeah, so I'll quickly talk about multi-core quantum computing, but I'll start being maybe a bit uh, pessimistic or negative. Uh, we need a lot of qubits to have a functional, useful quantum computer, and the reason is quantum computers to begin with are very slow. Qubits work at between microseconds and nanoseconds, which is much slower than what we're used to. But where they give us an advantage is that we can get, in some cases, exponential speed ups in the number of qubits, and I should say in the number of essentially perfect qubits that we have. It's somewhere between 50 and 150 qubits. We can already do tasks that are impossible for supercomputers, but none of our qubits are perfect. And if you're kind of optimistic, you'd say at around 1,000 physical qubits, we can have a nice machine. If you're more pessimistic, you'd say it requires 10 million. I personally am more on the optimistic side. But we're seeing ranges that are way beyond what we have today, and these qubits need to be connected in a way that allows them to be entangled together. We need everything. Essentially, we need the ability to entangle the entire system, and in order to do that, we need quantum information to flow between these qubits, and that means that if we're trying to build a machine that's made up of small quantum computers, we need to exchange quantum information. And this is a very difficult task. It's also a bottleneck that we're creating within the system. And so when I talk about multi-core quantum computers, I am not talking about having many quantum computers that are connected through an HPC or through a classical communication bus. I am talking about computers, small cores that are connected through a quantum bus that allows the exchange of quantum information. We need to connect, like I said, it's very hard to scale, or maybe I'll go back and I'll say it's very hard to scale monolithically. It's very hard to put 1 million qubits on a single device. It's hard to even put 100 qubits on a single device. And so we need to have lots of devices, and we need them to talk to each other. And there's essentially two ways that they can talk to each other. One is through, let's call them standard communication channels that exist within the system. And if we take the analog of that, you can think of your CPU on your machine either having like 5 CPUs on the same chip and them communicating with each other, or you can think of the CPU in your machine talking to the memory. And remember that in a quantum computer, the memory and the QPU, they're not two distinct things. They're the same. And so we can think of a small scale but modular solution where there's different components. And then we can think large scale, which is like an HPC where the interconnects are optical. And it's going to be incredibly hard to get to 1 million qubits without optical interconnects. And this is very unexplored. It's unexplored in terms of hardware, and it's even more unexplored in terms of software. And so there's two big questions that for us is one, what can we learn from HPCs who've been doing these kinds of, handling these communication bottlenecks for many years, and then how do we integrate it with HPCs, and how does a quantum computer work with an HPC? And we've heard a lot about that, so I'll say less about that. Just so we have a feeling for what the state of the art is, IBM currently announced a 433 qubit machine. IonQ has 25 qubits. What's nice about that 25 qubit machine is they're not perfect qubits, but they're a lot closer to perfect than other machines. And so we can really think of this as a computational power of almost 25 qubits. Rigetti have 80. Other companies have sort of just selected a few random ones, but other companies boast similar numbers. We're nowhere near 1,000. We're definitely nowhere near 1 million. And most roadmaps require a modular solution at some point. The sort of most optimistic ones are with solid state qubits who believe that they'll go to modular solution. They'll step outside the fridge, let's say, at about 1 million qubits. But even within the fridge, like I said, having your CPU connected to your memory, those kinds of things, you still have to have a modular solution. In terms of going into optics, the leader currently is ion traps, but state-of-the-art experiments can connect 1 qubit ion traps at a rate of about 200 hertz. So we're talking about something that is extremely slow. In these kinds of ion traps, the sort of decay time or decoherence time is about 1 second. And so 200 hertz means we're working at about 200 times the total like death to the computation timescale. It's not great. But you can still try and work around it with various techniques. And then getting to workflow, there's almost no work that's been done on the workflow. So there is a quantum MPI. So we just heard something about MPI and the quantum version of MPI, a little bit of work done by Microsoft. At Entangled Networks, we've built a distributed quantum computing compiler. And what we showed there is that once you take the compilation and you really look at the multi-core features, you can significantly reduce the overheads, but there are still quite a lot of overheads. And then there are a few simulators that can kind of simulate these networks, but they're mostly focused on the internet. They're not focused on something like an HPC. And then in terms of the challenges that we're facing, I think the biggest ones is that or one of the biggest ones, that, at least related to workflows, is that we really do not understand how information is going to be passed from the user who's writing the quantum program down to the machine. And there's no instruction set architectures. There are no standard intermediate representations. The representations we use today, things like Qiskit, are incredibly low level. And if we're imagining a computer that is multi-core, now we're adding an extra level of complexity to the programmer who's writing code at the low level, at the very low level. They need to now understand how to handle bottlenecks. They have to understand how to handle a non-deterministic process that spreads entanglement in the system. It's incredibly hard, and so we need intermediate representations. We need to understand what the compilation chain will look like on a real machine that, at some point will also include error correction. And once you have error correction, you're not going to sit there and program every single error correction operation by hand. That's usually done, down the chain. It's not something that the programmer should even be aware of. So a lot of work on workflows that needs to be done. So I'm more putting problems and solutions here, but yeah, thanks.